this video, we're going to talk about the graphs of the remaining 4 trigonometric functions, specifically the cosecant and secant functions, and then also the tangent and cotangent functions. Cosecant and secant are very closely related to their reciprocal functions. So knowing how to graph sine and cosine, knowing the values for sine and cosine, is going to be very important for these two graphs. It's also going to be important for tangent and cotangent because we're specifically going to get the values for the ordered pairs from what we know about sine and cosine. So let's start with cosecant and secant. So because of the reciprocal definitions, how we define cosecant and secant in terms of sine and cosine, because of this, cosecant is going to be undefined whenever our sine is 0, and secant is going to be undefined whenever our cosine is 0. So remember, cosecant is defined as 1 over the sine, and secant is defined as 1 over the cosine. So at any location where sine is 0, cosecant would result in division by 0, so it'll be undefined. Anywhere where cosine is 0, secant will result in division by 0, so it will be undefined. Now this is going to happen multiple times because of the nature of the unit circle, because we continue around and find repeat values for each of our trig functions, specifically our sine and our cosine. We're going to have multiple locations where sine and cosine go to 0, and hence where these two functions end up being undefined. Now division by 0, and something being undefined from the standpoint of division by 0, corresponds to a vertical asymptote on a graph. And again, because this is going to happen at multiple locations as we continue around the unit circle, we're going to have multiple vertical asymptotes on these graphs. Now also, because we have these asymptotes, we have locations where the graphs are going to hug this vertical line and then increase and decrease without bound. For this reason, these particular graphs have no amplitude. So we defined amplitude for sine and cosine as the height of each of those waves. How far up we go to the maximum and how far down we go to the minimum from that central line. Well, in this case, because the graphs increase and decrease without bound as they approach these asymptotes, we don't actually have a true wave height. So there isn't actually going to be a defined amplitude for cosecant and secant. Now, in order to graph these two functions, we have to be able to graph the reciprocals of them as well. So cosecant is always going to be graphed on what we call the cusps of the sine graph, and then secant is always graphed on the cusps of the cosine graph. Think of the cusps as those maximum and minimum points where we curve and turn around. Those are going to be the cusps of those wave graphs. So let's start with our cosecant function. Again, cosecant is defined as the reciprocal of sine. So knowing the values for sine, that's going to then give us the values for cosecant. So when we have an input of 0 radians, again, we're thinking of radian measures along the unit circle as our inputs. At an input of 0 radians, the value for sine we know to be 0. When we get to pi over 2, the value for sine is going to be 1. When we get to pi, sine is 0. And then we go down and minimize at -1. And then when we come full circle, we get back to a sine value of 0. Now these are not the actual values that we're going to graph though. From these, we want to get our cosecant. So sine, again, cosecant is defined as the reciprocal of sine. So cosecant, which is 1 over sine, in this case sine of t. Cosecant at 0 radians is going to be 1 over 0, which is going to be undefined. So that's going to be one of the locations where cosecant is undefined. Now once we get to pi over 2 radians, cosecant is 1 over our sine, so 1 over 1, which is also going to be 1. Once we get to pi, sine is 0 again, so 1 over 0, again, it's undefined. Once we get to 3 pi over 2, 1 over -1 is going to give me -1. and then come back full circle to 2 pi when sine is 0, 1 over 0 is going to be undefined. So this table is slightly misleading. It makes it look like there aren't going to be actually many points on the cosecant graph, and that's not actually going to be the case. But these locations where things are undefined, these are going to correspond to key features on the cosecant graph. What we want to know is what's happening around these locations. So wherever we have something that's undefined, that's going to correspond to a vertical asymptote. So let's label what we have so far. We have key y values at 1 and -1. So 1, -1, and then 0 in the middle. Okay. And then let's label our radian measures along the x-axis as well. So pi over 2, and then pi, and then 3 pi over 2, and then 2 pi, and of course, again, we're starting at 0. Now, anywhere where the cosecant is undefined, based on the sine definition, this possibility for division by 0, those are going to be locations where we have a vertical asymptote. So at 0 radians, we have a vertical asymptote. Remember, we always graph them as dotted lines because they're not really there. Technically, there's nothing there at that location. Then we also have them at every single multiple of pi. So this is related to the domain for cosecant. Cosecant is undefined at all locations that are multiples of pi, for any input that's a multiple of pi. And so on and so forth. So 3 pi, 4 pi, 5 pi, pi, -2 pi. Just like the sine function, this graph is going to continue indefinitely, periodically, forever and ever in both directions. Now, the actual locations where we have values, once we get to pi over 2, the sine is 1 and the cosecant is also 1, so they actually have a common value. And then once we get to 3 pi over 2, our cosecant is going to be -1, and again, they have that common value. So here's what's actually happening. Let's trace in the sine graph. But let's just put it in as a dotted line because, again, it's not actually there, just like those asymptotes aren't actually there. So here's our sine graph. It's going to look something like that. And notice those locations, again, where we have an asymptote, those are the locations where our sine graph is going to cross that central line. Now, what's happening with the actual cosecant? Because we've only got 2 actual points graphed here to represent our cosecant. Well, let's look at the unit circle. So for instance, once we get to pi over 6, what's the value for cosecant going to be? Well, at pi over 6, our sine is going to be 1/2. So if we were to take the cosecant, we take the reciprocal of that, the reciprocal of 1/2 would be 2. So at pi over 6, which is somewhere over here, we have an ordered pair maybe about right there. And then as we approach pi over 2, we get closer and closer and closer to this particular point. So as sine gets closer and closer and closer to 1, its reciprocal cosecant also gets closer and closer and closer to 1. Same kind of thing as we continue from pi over 2 to pi. So suppose once we get to 5 pi over 6, which is about there. Again, the sine is going to be 1/2, so the cosecant, its reciprocal, would be 2. So we essentially have this kind of behavior. We have something that's going to look like that. But those vertical boundaries, vertical asymptotes, remember, we never touch them, we never cross them. Now, same kind of thing once we get past this particular vertical asymptote. But now, because our sine values are negative, when we take the reciprocal, we also have negative values. So same kind of thing, but now we're below the x-axis. And so these branches, these separate branches, represent the branches for the cosecant graph. And just like this is one period of the sine graph, this also corresponds to one period of the cosecant graph. So having the sine graph here, using it as sort of a guideline, is going to make it a lot easier to graph the cosecant. If you can go ahead and put your sine graph on there, wherever the sine crosses the central line, that's where we have asymptotes. And then wherever sine hits a maximum or minimum, that's going to be the location where you graph one of the branches for the cosecant graph. Now, as we look at these, they look kind of like parabolas, right? These are not parabolas. Parabolas increase diagonally indefinitely in either direction, whereas these graphs, these curves, are bounded by these asymptotes. So with respect to shape, they look kind of similar when we're only looking at a small portion, but keep in mind they are not the same thing. This is truly a U-shaped graph, whereas a parabola continues out, and so it ends up being a little more V-shaped. So keep that in mind. Now, what about secant? We're going to see similar kind of behavior with secant. Secant is the reciprocal of cosine. So let's look around the unit circle and let's look at our cosine. So when we're at 0 radians, our cosine, our first coordinate, is going to be 1 on the unit circle. When we get to pi over 2, our cosine goes to 0, and then -1 at pi, and then we go back to 0 at 3 pi over 2, and then we make it back full circle to where our cosine is 1. Now, secant, again, is defined as the reciprocal of cosine. So when cosine is 1, 1 over the cosine is going to be 1. When cosine is 0, 1 over the cosine is going to be undefined, so similar to what happened with the cosecant. At pi, when cosine is -1, 1 over -1 is going to be -1. 1 over 0 is going to be undefined again. And then once we get to 2 pi, our cosine goes back to 1. 1 over 1 is going to be 1. So similarly before, we have the same key values on the y-axis at 1, -1. Same key radian measures as before, so let's put those in. 1, 2, 3, 4. So this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi, and of course 0. But in this case, we have vertical asymptotes at odd multiples of pi over 2. Those are the locations where cosine goes to 0, so those are the locations where our secant is going to be undefined. So they're at pi over 2 and at 3 pi over 2. Now, what about our actual ordered pairs? Well, they're at 0 radians. The secant is going to be 1. It shares a common point with the cosine. At pi radians, our secant is -1. And then at 2 pi radians, we go back to a secant value of 1. Essentially, the same thing that happened with the cosecant is going to happen here for the secant. Put in a guideline of the cosine graph. Again, we notice those common points, and notice that wherever the cosine graph crosses through its central line, that's where we're going to have an asymptote for our secant graph. And we're going to see the same kind of behavior. So as we approach those asymptotes, our secant value is going to either increase without bound or decrease without bound. Now, unlike the cosecant graph where you get 2 full branches, notice here we get a branch and then 2 half branches. And that's just because we're graphing from 0 to 2 pi. If we graphed a different interval, we would have full branches. So suppose we graphed from pi over 2 to 5 pi over 2, which would be our next key value. That would give us another asymptote, which means we could continue the branch. But if the idea is we always want to graph from 0 to 2 pi, at least whenever possible, we're going to get an image that looks like this. So just like the sine and the cosine graphs have the same shape, they just look like one another kind of shifted. Same kind of thing for the cosecant and the secant graphs. They essentially just look like one another, but shifted. So let's talk about how you would graph transformations of these particular functions. Here's the general rule, something that will make your life a little bit easier. If you're going to graph a secant, I want you to pretend for a minute that you're graphing the corresponding cosine. If you're going to graph a cosecant, pretend that you're graphing the corresponding sine. If you can take all of those transformations represented as part of the actual graph that you have and put them on your graph for either sine or cosine, then all you have to do is use the guideline that sine or cosine provides and fill in the shapes for secant and cosecant. So for this first one, we're going to graph y is equal to 3 times the secant of 2x. So you may want to put parentheses around that if that helps. That's going to be the input for our secant. Well, secant is the reciprocal of cosine, so their graphs are very closely related. So this is ultimately the function that I want to graph, but in order to graph it, I'm going to start by graphing the associated cosine graph, which is 3 times the cosine of 2x. I want to graph this, and if I can graph this function, then everything I get from this function will give me what I need to graph the secant function. Okay, so suppose we're graphing this one. Well, we need a couple different things. We need to know the amplitude of this graph. It looks like there's going to be a period change because, again, this is going to be our A, this is going to be our B, just as before. So the A is going to correspond to our amplitude. That means the cosine graph is an amplitude of 3. Be careful here, though. When we identify the amplitude for the secant, the corresponding secant graph, the secant doesn't have an amplitude. Because remember, amplitude represents the height of the graph. Secant increases and decreases without bounds, so it doesn't have an amplitude. But if we're graphing the cosine as a guideline, the cosine we graph is going to have an amplitude of 3. We don't have a vertical shift, so that means we increase to positive 3, we decrease to negative 3, and then we have that central line at 0 in the middle. Okay, now we also have a value for b, which changes our period. If cosine has a period of 2 pi, then so does secant, because again, they're closely related. One's defined in terms of the other. So our period is going to be the original 2 pi divided by this coefficient of 2, which is going to give us a new period of pi. So not only is that going to be the period for our cosine, it's also going to be the period for our secant graph. So whereas a normal graph, standard cosine, standard secant, repeats after 2 pi units, this graph is going to repeat in half the time, only pi units. Now, do we have a phase shift? Do we have a number added or subtracted onto our variable? In this case, no, so that doesn't apply. Do we have a vertical shift? Well, no, in this case, that doesn't apply either. So we've indicated what's going to happen with the amplitude, and we have our new period. Now, just like before, we want to determine what the increments are going to be over which we graph. And we're starting with the cosine graph in order to get the secant graph. So everything we did to graph cosine, we're going to do here. So because the period is pi, the increments are going to take that period, divide it into 4 equal parts, and that's going to be the number of units apart for our individual increments. So we have 4 equally spaced marks, and each one is pi over 4 units away from the previous one. Now, because we haven't shifted anywhere, we know we're still starting at 0. The only way that changes is if we shift to the left or shift to the right. But here we're starting at 0 because we haven't shifted. We just reach pi by the time we complete a cycle rather than getting all the way to 2 pi. And then each of these units is going to be pi over 4 units apart. So 0 to pi over 4, and then 2 pi over 4, otherwise known as pi over 2, and then 3 pi over 4, which doesn't reduce, and then 4 pi over 4, which takes us to the end of our period. Okay, so now we want to put in the cosine graph following this particular set of coordinates. So cosine, we know, starts at its maximum and then drops down to the minimum and then goes back up to its maximum. But it's just a guideline, so I'm going to put it in with a dotted line because, again, it's not really there. Okay, now once we have that cosine, we want to get the corresponding secant. So first thing we want to get those asymptotes. That's going to be an important place to start. We know wherever cosine is 0, secant is undefined. So wherever we have an intersection with that horizontal line, with that central line, that's going to be a location for our asymptote for our secant graph. So in this case, our two secants for our standard period are going to fall between pi over 4 and 3 pi over 4. And then wherever our cosine hits a maximum or a minimum, we have a shared point with our secant graph. And then we can just fill in the branches from there. And that is going to be our secant graph. Now we have one additional question. What is the range? Specifically the range for our secant graph. Well, the range for the cosine would be everything from -3 to 3. Normally we go from -1 to 1 because cosine is defined on the unit circle. But once we change the amplitude, think of that as almost making the circle bigger in a sense. It's now like a circle of radius 3. So our cosine minimizes at -3 and it maximizes at +3. Well, if we look at the secant though, notice the secant is the other points beyond those boundaries at 3 and -3. So the secant corresponds to everything above +3, corresponding to also 3, and then everything below -3, including -3. So our range for our secant is going to go from -infinity to -3, so everything down here below -3, but including -3. And then also everything above +3, yet again including +3. So that's going to be our range. And we know, of course, the domain is going to exclude any values where we have asymptotes. And in this case, it's going to be odd multiples of pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and then so on and so forth. So if you can get the cosine graph or the sine graph, depending on which function you're looking at, that's going to be most of the work. So doing that part, once you find those points of intersection with the central line, those are going to give you the locations for your asymptotes, and then you can just fill in your graph from there on the cusps of your sine or your cosine graph. So there's a secant. Let's do a cosecant. Okay, so we want to graph y is equal to the cosecant of the quantity x minus pi over 4 plus 3. And again, we want to identify the amplitude, the period, the phase shift, if there's a vertical shift, and ultimately the range, and we'll wait on the actual graph to do that part. So here, because we're graphing a cosecant, we're going to graph it using the sine as a guideline. So in addition to graphing this, we want to graph its corresponding sine function, which is going to be the sine of x minus pi over 4 quantity plus 3. So this will be where we'll start. We're going to start with our sine. Okay, so that means we have a value for C and we have a value for D. Now we don't have a coefficient here, so it's understood to be 1. But again, be careful with your amplitude. We're talking about the amplitude for cosecant. So sine has an amplitude of 1. That means we're going to mark a maximum at 1 and a minimum at -1 for the actual sine, and the central line is there at 0. Is it? What about this 3? What do we do with that? Well, we have to actually shift all of these, right? So the central line is going to shift from 0 to 3, and then 1 unit up from there, which is going to take us to 4, and then 1 unit down, which is going to take us to 2 because of that shift. What about the amplitude for our cosecant though? Is it going to be 1? Remember, it doesn't have an amplitude. There is no highest or lowest value for our cosecant. It increases and decreases without bound. So although the sine has an amplitude of 1 and everything is shifted up 3 units, the cosecant does not have an amplitude. So we can just put NA there. Now, do we have a period change? We don't have a value for B, which means we haven't changed the period. So that means the period for both the sine and the cosecant is going to be 2 pi. Now we do have a phase shift. That's corresponding to our value for C. So since we don't have a value for B, C divided by B is just going to be whatever the value for C is. Now because it's subtracted, remember that's shifting to the right. So we think of C as being a positive value. So we're going to shift to the right pi over 4 units. And you might just want to put an arrow, make sure you know which direction you're going. And then our vertical shift is going to be positive 3 which is going to be up 3 units. We've already put that on the graph. So let's graph our sine. What do we need now? Well, we know the period. We need to determine what the phase shift is going to do to that period. So 2 pi, our period, is going to be divided up into 4 equal parts. So 2 pi divided by 4 is going to be pi over 2. That's going to be how many units apart our individual increments are. But the question is, where does our graph start? What's the cycle going to be over which we graph? Well, we're shifting everything pi over 4 units to the right. So what's the impact on our standard cycle from 0 to 2 pi? Well, let's see what it's going to be. So 0 is less than or equal to our input, which is also less than or equal to 2 pi, standard cycle. Okay. Add pi over 4 to both of these endpoints. So that means pi over 4 is less than or equal to x. We can write 2 pi as 8 pi over 4. And so when we add pi over 4, that's going to take us to 9 pi over 4. So this is going to be the new starting point, and this the new ending point of our graph. So we're going to start at pi over 4, and then moving by equal increments. We already determined each of these is going to be pi over 2 units apart from the previous one. And then we're going to end at 9 pi over 4. Okay, now here, if we can count by pi over 2, we can do that. Here's a thought: if you don't want to have to write out algebraically how you find each tick mark, we're counting by pi over 2, but it's the same thing as counting by 2 pi over 4. So maybe just count by 2 pi over 4 so that we already have that matching denominator. So pi over 4 plus 2 pi over 4 would take us to 3 pi over 4. Well, 3 pi over 4 plus 2 pi over 4 would take us to 5 pi over 4. 5 pi over 4 plus 2 pi over 4 would take us to 7 pi over 4. And then 7 pi over 4 plus 2 pi over 4 takes us to 9 pi over 4, which is where we're supposed to end our cycle. Okay. So what does this mean for the actual axes? Where are the actual axes in this case? Well, all of our y values that we're graphing on are positive, which means our x-axis is somewhere down here. And we're starting at pi over 4, a positive number, which means our y-axis is somewhere over there. So just keep that in mind. As we graph, we're technically graphing in the first quadrant of our coordinate plane, of the xy plane. Okay, so we're graphing a cosecant, which means we're going to start with the corresponding sine graph. So sine starts at the center line, increases to its maximum, goes back to the center line, decreases to its minimum, and then goes back to the center line. Now each location where sine crosses its center line, that's where we're going to have an asymptote. So let's put in those asymptotes. In this case, we get to graph 3 of them. Okay, and then we're going to graph our cosecant on the cusps of our sine. And that's going to be our cosecant. So now let's identify the range of our graph. Keeping in mind, again, that dotted line for sine is not there. We're just looking at those branches representing the cosecant. So the sine would go from 2 to 4. Those will be the values that we omit when we're looking at the range for the cosecant. So we have all the y values we want, 4 and above, and then all the y values we want, 2 and below. So our range is going to be negative infinity to 2, including 2, union 4 to infinity. So the situation we didn't look at, one to keep in mind, is remember what happens when we change the period and we have a phase shift. It becomes more important than ever to figure out what the actual cycle is going to be. So anytime you want to graph a secant or a cosecant, just start with the matching sine or cosine. If you can get that graph, then all you have to do is then put in your asymptotes and then graph the branches on the maximum and minimum locations for your sine or your cosine. So now let's talk about tangent and cotangent. So secant and cosecant are related to sine or cosine, one or the other. Tangent and cotangent require us knowing both values at the same time. So tangent is specifically defined as the ratio of sine to cosine. So for that reason, tangent is going to be undefined whenever cosine, whenever that denominator is 0. And then cotangent is the reciprocal, so it's the ratio of cosine to sine. So it's undefined whenever sine is 0. And as with our secant and our cosecant, this corresponds to a vertical asymptote on those graphs. And since again there are multiple locations where sine and cosine go to 0, there will be multiple asymptotes on each of these graphs. Now tangent and cotangent, the biggest difference between these graphs and the other 4 graphs we've looked at is their period. Tangent and cotangent repeat faster than sine and cosine and then cosecant and secant do. They actually have a period of pi. But as with cosecant and secant, they also have no amplitude. We're going to find from these graphs that they continue indefinitely in both directions. They increase without bound, they decrease without bound, so they don't have an actual wave height, they don't have a defined amplitude. So let's determine what our sine, cosine values are and then the respective tangent and cotangent values. Now you'll notice I've kind of spaced things out a little bit differently. We're not graphing all the way from 0 to 2 pi for one. That's because the period is pi. So we don't need to go all the way from 0 to 2 pi in order to get the full picture. We just need one period, which takes us from 0 to pi. But I've also included some negative values here, and we'll come back to those in just a minute. For now, let's just start at 0 radians where we normally do. And we want our values for sine and cosine as we go from 0 to pi over 4 to pi over 2 to 3 pi over 4 to pi. And again, we're using additional values in the middle because we travel across the period a little bit faster. So when we're at 0 radians, our sine, our y-coordinate, is going to be 0, and our cosine, our x-coordinate, is going to be 1. Now when we get to pi over 2, our sine is root 2 over 2, our cosine is also root 2 over 2. When we get to pi over 2, our sine is going to be 1, and our cosine is going to be 0. Now as we go into the second quadrant past pi over 2, now we have negative x values. Okay, so our sine is still positive. At 3 pi over 4, our sine is going to be root 2 over 2. But our cosine is now negative. It's going to be negative root 2 over 2. And then once we get to pi, our sine is going to be 0, and our cosine is going to be negative 1. So let's look at the values for tangent across these particular radian measures. Okay, so when we're at 0 radians, tangent is defined as sine over cosine, so it's going to be 0 over 1, which is 0. When we're at pi over 4, sine and cosine are the same. Don't be alarmed by these numbers. Sine and cosine are the same, which means when you divide them, you get a result of 1. Now once we get to pi over 2, sine over cosine is 1 over 0, which is then undefined. When we get to 3 pi over 4, sine over cosine, equal and opposite, so one divided by the other is going to be negative 1. And then when we get to pi, we're going to have another value at 0. So let's put all of that on our graph for tangent, and let's see what we're looking at. Okay. So 0 to pi over 4 to pi over 2 to 3 pi over 4 to pi. And it looks like we've got key values at 1 and negative 1 yet again. So here's 1, here's negative 1, here's 0, here's 0. And then we're counting in this case by pi over 4 each time. So I'm still just going to label pi over 2 and pi, but I'm going to put those intermediate tick marks in there as well. Keep in mind that's pi over 4 and then 3 pi over 4. So when we're at 0 radians, our tangent has a value of 0. And then when we're at pi over 4 radians, our tangent has a value of 1. And then when we get to pi over 2, it's undefined, which means we now have a vertical asymptote. Now when we get to 3 pi over 4, we're at -1. And then at pi, we're at 0. So we end up increasing, hugging that side of the asymptote over here, and then from -infinity, increasing on that side of the asymptote. Now this is technically a full period of tangent, but here's the problem. If you keep in mind how this graph would repeat, well, we'd get something like that, and then we'd have another asymptote, right? Which means that standard period from 0 to pi doesn't actually give us the full picture in the sense that we get a whole branch. This is similar to what happened with the secant. So with the secant, remember we got one full branch and then 2 half branches as we went from 0 to 2 pi. So the half branches were a little troublesome, but because we were able to get one full branch and see the shape, these weren't too much of a problem. Here on the tangent graph, if we just graph from 0 to pi, we get 2 half branches and we don't have a single full branch. So what we're going to actually do here for tangent is we're also going to look at some radian measures that would take us backwards in the negative direction. In other words, if you were to start at 0 on the unit circle and then rotate backwards into the 4th quadrant, but not representing 270 to 360, instead representing 0 to -90 degrees. Think about it that way, or negative pi over 4 and negative pi over 2. So at those locations, what would you get for the sine and cosine? So negative pi over 4, remember that's going to be coterminal with 7 pi over 4. So it's 7 pi over 4. Our sine, our y-coordinate, is going to be negative root 2 over 2. And then our cosine, our x-coordinate, is going to be positive root 2 over 2. We take that ratio, sine over cosine, it's going to give us a -1. And then at negative pi over 2, which is coterminal to 3 pi over 2, our sine, our y-coordinate, is going to be -1, and our x-coordinate is going to be 0. So we end up with another location where the function is undefined. So let's add that into the graph. So this would be negative pi over 2, and that's going to be the location for an additional asymptote. And so there's the asymptote, and then at negative pi over 4, the value for tangent is -1. So we would continue that branch down there. So rather than graphing from 0 to pi, when we look at tangent, we're specifically going to graph from negative pi over 2 to pi over 2. That's going to be our standard period when we graph our tangent. Again, so that we can get that full branch rather than half a branch and then another half of a branch. This is going to allow us to have a full picture. So this particular range of values is going to give us our standard period that we graph whenever we graph tangent. And this is specific to tangent. Tangent is the only function where we have this problem, so it's the only function where we're going to worry about graphing from that point of view. So now let's look at the cotangent. We already have all the values for sine and cosine. Cotangent is defined as cosine over sine. And again, let's start at 0 radians. Let's see what happens. So there at 0 radians, cosine over sine is 1 over 0, which is going to be undefined. Okay, at pi over 4, cosine over sine is going to give us 1. At pi over 2, cosine over sine is 0 over 1, which is 0. At 3 pi over 4, negative root 2 over 2 over positive root 2 over 2 is going to give us -1. And then at pi, -1 over 0 is going to be undefined again. So let's see what that looks like on our graph. Again, we've got key values at 1 and -1. That central line at 0. And then again, we're counting by pi over 4, going all the way out to pi. So here's pi over 2, here's pi. And notice in this case, we have asymptotes at 0 and at pi. Those are going to be the locations where we have asymptotes for our cotangent. So let's put those in. So here's 0, here's pi. And then the actual ordered pairs we get to graph at pi over 4, our y value is 1. So at pi over 4, we're at 1. At pi over 2, we're at 0. And then at 3 pi over 4, we're at -1. And so cotangent decreases over this interval. And that's going to be our graph for cotangent. Now notice for this particular function, we do get a full branch if we just graph from 0 to pi. So for cotangent, that is going to be the interval we graph. So for cotangent, we'll specifically graph from 0 to pi. Now what I want you to also notice is cotangent and tangent seem to be closely related in terms of the shape of their graph. If you were to take the cotangent graph and reflect it vertically and then shift it a little bit, you would have the tangent graph, and vice versa. The same kind of thing happens with sine and cosine. The same kind of thing happens with cosecant and secant. If you were to take them, flip them, shift them a little bit, the shapes are otherwise the same. So that's going to be an important thing to keep in mind as you graph. What's also important to keep in mind is their differences. So notice tangent, if you look at one branch, the branches for tangent are increasing as we look left to right. The branches for cotangent are decreasing. And then most important is going to be the location of those asymptotes. Tangent graphs from -pi over 2 to pi over 2 for the standard interval, and those are going to be the locations where we have our asymptotes. Cotangent is going to graph from 0 to pi, and those are going to be the locations of those asymptotes. So when in doubt, if you can't remember where the asymptotes go, look at those quadrantal angles at 0, at pi over 2, and then at pi, and determine what the values would be for your tangent, for your cotangent. At any of the locations where one of them is going to be undefined, that's going to be a location for an asymptote, and then you're going to find asymptotes at regular intervals after that. So that'll be something helpful to look at. So let's do a couple of transformations for these. Okay, so we want to graph y is equal to 3 times the tangent of pi over 4x, put parentheses around that, and again identify its amplitude, its period, and then a phase shift or vertical shift as well. So let's start with the amplitude. Do we have an amplitude? Well, remember, tangent increases and decreases without bound. It has no amplitude. So there is no amplitude here. So what is this value 3 going to do? Well, think of this as just a stretch. It may help to think of that as just a stretch. Where we mark 1 and -1 on the standard tangent graph, those are instead going to be 3 and -3. So that's how those values are going to affect things. And again, still got that central line at 0. Now what about our period? Now A, B, and C, D, they still behave the same way here, but remember the period for tangent, the original period is different. So here, when we use our B, we're dividing that into our original period of pi, because tangent has a period of pi, not 2 pi. So pi divided by pi over 4, that's going to be pi times 4 over pi, and so we have that common factor that divides out, and that's going to be 4. So our period here is going to be 4. Now we're not adding or subtracting anything onto x, so there is no phase shift, and we're not adding or subtracting a term outside of the function, so there's also no vertical shift. Now here more than ever, we're going to have to be careful about graphing the right cycle. Where does the cycle start? Where does the cycle end? Because remember, it doesn't go from 0 to 2 pi. It doesn't even go from 0 to pi. Tangent is special. The standard interval for tangent is going to go from negative pi over 2 to pi over 2, because those are the values over which we get a full branch of our tangent graph. So when we set up that inequality to determine the beginning and the end point for our cycle, we need to indicate that we're starting at negative pi over 2 and we're ending at pi over 2. So negative pi over 2 is less than or equal to our input, which is pi over 4x, and that's also less than or equal to the standard endpoint at pi over 2. So we can divide pi over 4, or alternatively, we can multiply by 4 over pi, same effect. Okay, so those common pi's are going to cancel out. 4 divided by 2, a negative is going to be negative 2. And then 4 divided by positive 2 is going to be positive 2. So this is going to be our interval from negative 2 to 2. Now, when we graphed the original tangent, we graphed it where it was truly starting to the left of that central line. If you want to graph it that way, in this case, negative 2 to 2, you can graph it with a negative 2 over here and a 2 over here if you want. Or you can do what we did before with the other graphs and start your cycle on the vertical line and then just indicate where the actual y-axis is. Ultimately, it's up to you. It's all about labeling. Just make sure things are labeled, and then based on where your labels are, that's where you're going to graph. So just for the sake of being consistent with the other things we've graphed, I'm just going to start the cycle there on that vertical line, which in this case is no longer going to correspond to the y-axis. So the graph is going to start at negative 2, and then it's going to end at positive 2. Now we're also counting by 4 units here, but notice it's a little bit different. We went from negative pi over 2 to pi over 2 and counted by 4. And then we just had marks in the middle as well. But we weren't counting by pi over 2 originally. Here it would be by pi over 4 originally. So 1, 2, 3, 4. And we're going from negative 2 to 2. And here our period is 4 units. So 4 units between negative 2 and 2. 4 equally spaced increments. And so if we divide our 4 into 4 parts, that means we're counting by 1 increment each time. So negative 1, 0, 1, and then 2. Where our cycle starts, that's where we have our vertical asymptote. Where our cycle ends, that's where we have our other vertical asymptote. And then our tangent graph increases across that interval. So there at negative 1, we're there, and then we cross our central line, and then we're increasing. So that is going to be a single period. Now, keeping this in mind, this would then be the new location for our y-axis. If we did want to, in fact, start with the axis we have drawn and not graph to the left of that, then our new y-axis is going to be at that particular location. Okay, let's look at one final example. Let's do a cotangent. Okay, so cotangent is going to graph from 0 to pi. Okay, tangent is the only one that graphs from negative pi over 2 to pi over 2. Now here we have a number added on inside and outside of the function. So we'll call this C and we'll call this D. Now amplitude, do we have an amplitude? Remember cotangent, tangent, increase, decrease without bound, they don't have an amplitude. The period is not changed because there's no coefficient in front of the x, so we're just going to keep the standard period for cotangent, which is going to be pi. Now we do have a phase shift because we're adding on this term to our input x. Because it's positive, because we're adding, it's shifted in the negative direction. So our phase shift is going to be negative pi over 4, which is going to shift our graph to the left. And then the addition of 2 on the outside is going to shift us up 2 units. Okay, so let's go ahead and label the vertical axis based on our vertical shift. So otherwise, we would go with key values at, excuse me, let's move that, -1, 0, and 1. All of that is being shifted up 2 units. So think of shifting that central line there at 0. It was at 0, now we're shifting it up to 2. Because we don't have a coefficient in front of the cotangent, it's understood that our next values are just 1 unit apart from there. So we go up to 3, down to 1. Okay, so all of that is labeled. Now let's work on the horizontal part. So our period is pi. So from start to finish along our full cycle, we go pi units. But in this case, everything is shifted negative pi over 4 units to the left. So what's our cycle going to be? Well, the standard cycle for cotangent, so x plus pi over 4, is going to go not from 0 to 2 pi, but 0 to pi. That's the standard period for cotangent. So if we apply this transformation, subtract that pi over 4 from both of those endpoints, pi you can think of as 4 pi over 4. So subtract your pi over 4. It's going to take you to 3 pi over 4. So this is our new start point. This is our new end point. So I'm going to label this at negative pi over 4 and then count by a certain amount to take you to 3 pi over 4. Okay, now our period is pi over 4. We're dividing that into 4 parts in order to graph those increments. So it's going to be pi over 4 units apart to get from one mark to the next. So because we already have units that have a denominator of 4, we can just count. So negative pi over 4, add on pi over 4 takes us to 0. Add on another pi over 4. Add on another pi over 4, which will be 2 pi over 4, otherwise known as pi over 2, and then 3 pi over 4. And as long as we've graphed with the correct cycle and adjusted the cycle correctly, then we'll be able to just put our asymptotes at the beginning of the cycle and at the end of the cycle. Okay, now cotangent is a decreasing function, which means we start above and go below. Now there in the middle, that's where we cross our central line, but we're going to start above to the left and then go below to the right. And so this is going to be our graph. Okay, and as before, notice because we graphed on this vertical axis and it wasn't at 0, this is no longer the y-axis. So this is going to be the actual y-axis in this case, and we're also above the x-axis. So our actual x-axis is somewhere down here if we wanted to graph that. So that gives you a few examples of our different situations with our other types of functions. In general, all of the same transformations apply. Definitely be careful with tangent and cotangent just because the period has changed, and then tangent especially because in general our period is not going to start at 0, it's going to start in the negative direction. So just as with the sine and cosine graphs, it's going to be good to maybe take these particular functions, write them down on a clean sheet of paper, see if you can graph these functions again, identify all your transformations. Most important thing, regardless of what you're graphing, is your labeling. Start by labeling the x-axis and the y-axis, and past that it's just filling in points that correspond to the shape of a particular graph.